we talk about all the forces that we need to know, like gravity, and then normal force right here, and then tension and friction. Okay. So as I said, the most important thing for this, I mean, for solving problem in this chapter is so-called force analysis. Again, the key here is we want to know some, for example, sometimes we want to calculate the kinematic information, which is about like acceleration, right? Now, how do we do that? Basically, the way to do that is to be able to figure out the forces on the object so that we can use Newton's second law, which is F equal to ma. So that is critical that we can do a force analysis here. And so I'm gonna give you a series of examples about this force analysis and also about what do you do after that, okay, to solve problems. So I'll give you a bunch of examples, okay, on the on Newton's law problems, okay. So let's start from the simplest possible example. I'm gonna do it in a way that it goes from very simple problems cases to complicated cases, okay. So hopefully by seeing this series of examples, you can kind of see that how things go, you know, how we go from simple to complicated. So the first problem we have is going to be like this, okay. So this is the example one. I think I choose the black. Do you guys think black is okay? Maybe I'll use black for a little bit. So this example is the following. So you have a box. The box is simply staying at rest on the surface, on a surface, okay? Staying at rest. And we also know that the mass of the box is 3 kilograms. So the question is, what is the normal force on the box? Okay. I know this is a very simple problem, but I like to start from here, and then I use it to show you how to solve the problem. Okay. So as I said, any problem in Newton's law, you need to start from force analysis. Okay. So that means actually, when you remember I said each time you do a problem, right, you start from drawing a picture. In this case, we should start from something called a free body diagram. So a free body diagram is something that you like this. Okay? You draw the box here. Okay, you draw the object. Okay, this is the object you're interested in to find out the motion about. Okay, or to find out force about. So you need to draw the forces you have on the object. Okay, that's called free body diagram. Okay, now how do we do that? Remember what I said yesterday. You should always start from gravity because unless the problem specifies that this thing's in the space, mostly we assume that it's on the surface of the Earth. So there's always going to be gravity. Okay, so you draw gravity first. Okay. So draw it like this. Okay. So and I'll label it as mg. Okay. Now you should, after that, you should look for contact. Look for contact. Okay. Now in this case, we have contact with surface, right? So as we know, we have contact with surface, it's possible to have normal force and also possible to have friction. Well, this thing's not moving, so definitely there's no kinetic friction. And there's also no forces going along the horizontal direction, so there's no kinetic, so there's no static friction either. So basically there's no friction. The only force you have on the surface is just the normal force, okay? So the normal force is actually acting on the surface, right? On the contact surface between the object and the surface, but it's convenient to draw it so that it starts from the center, like here. Well, it's essentially we're like parallel shifting the vector so that instead of starting from the surface, we started from the center. But actually, it doesn't matter. Okay, the vector is still the same. So it's just a little more convenient to draw all the forces starting from a single point. Okay, so that's all, right? So we have gravity and we have normal force, and that's everything we have because there's no other contact to the object. There's no pushing or pulling force. There's no tension, nothing. So that's it. Okay, so with that, we can now, we're done with our free body diagram. So what is next? Okay, the next step is to set up a coordinate system, okay? It is important, not that much for this problem, but for problem in general. So we will set up a coordinate system like this. Normally you pick up the origin to be the center of the object so that all the forces start from there. And then mostly you set up the horizontal direction as your x direction and vertical direction as your y direction. So, and that's what we're doing here, okay? That's how we do that, okay? Now, for this problem, it's simple because all the forces are right on the y coordinates, you know? So there's no need for you to find the components of the forces because they're already on this axis. So this is like actually a one-dimensional problem, right? The next step is gonna be based on this free body diagram and then the two axes you have, write Newton's law. Remember, Newton's law is this, okay? Force equal to ma. And because normally we have more than one force, so it's sometimes convenient to write this, okay? So we understand this is the sum of all the forces, okay, equal to mass times acceleration. The sum equal to mass times acceleration, okay? So we can remember this is a vector equation and we cannot do vector sum or anything directly. So what we can do is break it down to the x component and y component, write them separately, okay? So along the x component, the equation would be the sum of the forces Fx equal to max. Along the y direction, it's going to be sum of the forces along the y direction, Fy equal to may, okay? So these are basically the kind of formula we actually use in solving any problem. We don't use this one, original one with vectors, but we use their components, okay? So, and for this specific problem, it's very simple because along the x direction, there's no force, so we don't need to worry about it. So we only need to consider the y direction, okay? So let's try to write down this one in this specific case. So on the left-hand side of the equation, you have total forces, right? So in this case, according to the diagram, we have two of them. So we have N, and then we have minus mg here, okay? So that's our total force. Notice that I put the minus sign here because I know this weight is going downwards, going to the negative direction. So I write this minus sign explicitly. So this mg here is always going to be positive. The mg here is going to be the magnitude. The sign is given by this by the minus sign I write here, okay? So this is my total force on the left-hand side, okay? This should equal to mass times acceleration on the right-hand side. So we have m times ay. So what is ay in this problem? What is the acceleration along the y direction? You can send me a message. I don't know why there's always doing that. Okay. What is the acceleration along the y direction? Just send me a message. Let me know. Give a guess. Okay. 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 I got a couple guesses here. Okay. The answer is there's no acceleration. Okay. See, the problem says staying at rest, right? Staying at rest means there's no motion. So certainly there's no acceleration. So the acceleration along the y direction actually is 0. Okay. Now some of you said 9.8. That was not right. Remember, 9.8 is the acceleration that only there for a free fall motion. Okay. When you have free fall motion, it's 9.8. Okay. So, but again, I appreciate you guys' response because these are very typical response here. And then a lot of people that are not here, they would have guessed the same thing. So this helps them to know they're wrong and why they're wrong. So it's actually 0 here. So this is just equal to 0 in this case. Okay. So and from there you can actually solve for the normal force, right? It's a very simple thing because n minus mg equals 0. That means n equals to mg, and that's it. Okay. So you have a 3 kilogram for mass, and then g is 9.8 meter per second square. Again, remember this one here is not a real acceleration for this problem. It's just a conversion factor convert mass to weight. Okay, so I have 3 times 9.8. Okay, so that you do this calculation, you get your answer. Okay, you got 29.7 Newton. Okay, so kilogram times meter per second squared is Newton. Okay, sorry, 4. 29.4 Newton. Okay. Again, this is how you solve a problem. This problem is really simple. You probably don't need to be in this class you can guess the answer, because when you have something there, right, like a normal force, you can guess it's just equal to weight to balance all the forces, so it'd be just weight. But again, this is the important thing to realize. This procedure here will help you to solve any problems in Newton's law. Again, we start from a diagram, we do free body diagram, and then we set up coordinate system, and then we write Newton's law along each direction. In this case, only one direction, and then we solve the unknown from the direction, okay, from the equation, okay. So any question about this one? Okay, let's do another one, okay. So this one's will be a little bit more complicated, okay. So we're gonna start to pull the object. Okay, we'll use a pulling force F. Okay, and then the F is gonna be just let's say we know the force. Let's say it's 5 Newton. Okay. Now we also say that still the mass is 3 kilogram, just like before. Okay. Now for simplicity, we'll say that there's no friction on it's frictionless. Well, we know it's not very realistic because most surfaces do have friction, but this is a simple case to start from. Okay, so it's frictionless with the pulling force F equal to 5 Newton and the mass is 3 kilogram. So our question here is, what is the acceleration of the object? Okay. Now we know there's going to be acceleration because when there's one force pulling it, right? So you have a force, and then there's certainly going to be acceleration. So that's what we want to find out. Okay. Again, we'll do the same procedure. This time I'll do a little bit faster because we already did this before. So again, we need to know how many forces we have on the object. Well, there's always gravity, that's always there. And then after that, we have normal force going to the opposite direction. And then, so because we have the contact to the surface, right? So from the contact, we know there's normal force. Well, the contact may also give us friction, but it says frictionless, so there's no friction here. And then we have this pulling force, which is given the problem. So again, I would drawing it from the center. So this F here. So we have 3 forces. We have one more compared with the last problem. Okay. Now we then do this coordinate system. X direction, Y direction. Okay. So these are 2 coordinate systems and coordinates. Okay. And then we make sure all the forces are along either X or Y direction. In this case, there's no force going other directions, so there's no component to worry about, just all the forces on the X or Y direction. We're good, okay? Now let's do Newton's law. Okay, again, the idea is you need to set up 2 equations for these, okay? So let's start from the first one, okay? Along the X direction, there's only one force, which is F. So just write F here, okay? We'll write M here as well. What about the acceleration? Okay, this is something we want to find out. So I'll just write A here, okay? Because there's no, we don't know it. So let's call it A. Along the Y direction, similarly, okay, we have 2 forces, one going up, one going down. So I have M minus mg. That's the total force, okay? So what is AY in this case, in the second case? Can you guys send me a message? Okay, I got something. Okay, yeah, there's somebody says 0. That's correct. Okay. Well, again, in this problem, it didn't really. It basically, I didn't write it down, but I told you guys there's a force that's going to move on horizontal direction. So there's no motion along the vertical direction, right? And you wouldn't expect any motion along the vertical direction, right? For this kind of a situation, right? You wouldn't expect this thing going up and down, right? With this force putting horizontal. So there's no acceleration along the y direction. So we have put a 0 here. Okay. So in this problem, we got 2 equations because we have 2. We use both of these. And what we want to find out is this one, A. So actually only the first equation is useful for us. But it doesn't matter, it doesn't hurt to set up two equations, set up all the equations using Newton's law, okay? So we only need the first one. So from the first one, we can see that acceleration equals to force divided by mass. So we just 5 Newton divided by 3 kilogram. So you go ahead and calculate it, you do the calculation, you get 1.67, okay? Basically, a lot of 6, basically. So Newton divided by kilogram is actually meter per second squared, okay? So that's our solution for this one, okay? Okay, I got a message. Let me look at it. Okay, yeah, you're right. A equal to 1.66, or if you run it up, it's going to be 1.67. Okay, that's good. Okay, so that's how we solve this one. Okay, again, the idea is very similar. We got one more force, but that's just give us one more equation, nothing more. Okay, so let's make it a little bit even, a little more complicated. Example 3. Okay, so this time it's still this thing pulling with this friction, with this F here, but we're gonna give it a we're going to say that this is not frictionless anymore, okay? It's going to be frictional, okay? So F equals to 5 Newton, M equals to 3 kilogram. And then let's say we have mu K, the coefficient of kinetic friction, equal to 0.1, okay? So again, we want to find out the acceleration, okay? So let's say the object is moving, okay? And then we want to find out acceleration, okay? So this problem is a little more complicated because we have a friction here, right? So let's do it again. So start from very beginning, we have a free body diagram. Now we start from gravity, it's always there, and then we look for contact. There's contact with surface, so we have normal force, and then we have friction. Well, because that there's kinetic friction, right? I mean, the coefficient of kinetic, so it's not frictionless, so there's definitely friction here. And because it's moving, right? So it's a kinetic friction, okay? And then we still have this pulling force F here, okay? So these are the 4 forces we have. We have 4 instead of 3 here, okay? Again, we do the coordinate system, X and Y. Okay, now we'll follow Newton's law here and set up equations along the X and Y direction, okay? Along the X direction, we have 2 forces instead of 1. So we have F minus Fk equals to ma, okay, where a is something we want to find out. On the y direction, we have n minus mg, and it's still equal to 0 because there's no motion, there's no acceleration. So these are 2 equations we have, okay? Now let's try to solve for a. So a is in the first equation, right? But we see there's an unknown here, which is fk. So in the first equation, we have 2 unknowns, okay? While the second equation does not have much because it does not give us any information about a and fk. So it seems like we need another equation here, okay? Because otherwise we wouldn't be able to solve the problem, okay? But if you remember what we talked about, there is a relation between the kinetic friction and normal force. We have Fk equals to mu k times n, okay? So almost always when you have a problem that requires kinetic friction, you need this formula. So that's always there. So we actually have 3 equations in this case, okay? Well, it looks a lot, but the way to solve them is not too bad, okay? Too hard. Again, let's look at the first one, right? We want to get A. That means we know Fk, right? So how do we know Fk? Now we see that it's given by the third equation here, Fk equal to mu k times n. So we can figure out n here, we know Fk. So how do we get n? Then we see the second equation, we have n equal, n is in there, so we can solve n first from second equation and go to the third one to get Fk, and then go back to the first one to get A. So that's going to be our logic. Okay? Again, as you can see here, the logic is to start from the something we want to figure out, the unknown, and then trace back until finally we can see what we can do here. Okay, so let's start from second equation here. Okay, we have n minus mg equals 0, so n equal to mg. So we already did it in the first example here. So that's going to be just 29.4 Newton. Okay, after that, we'll go back to the third equation to solve for Fk. And then we plug in mu k equal to 0.1. So 0.1 times 29.4. So we got 2.94 Newton. Okay, so that's the friction. Okay, and then we go back to the first equation to solve for A. So from the first equation, A, if you divide M on both sides, right? So A is equal to F minus Fk divided by M. Okay, so F is 5 Newton and Fk is 2.94 Newton and M is 3 kilogram. Okay, so again, plugging numbers, you have you do calculate, you have 5 minus 2.94, that's 2.06, okay, divided by 3 kilogram. Okay, so this gives you roughly like 0.97. Okay, with a little bit. Oh, I got a question here. Sorry. Okay, 0.69. Is that what you got? Okay, yeah. I don't have a calculator with me, so yeah, that's good. Let's write it down. Okay, 0.69. Newton divided by kilogram, so it's a meter per second squared. Okay. Okay, so that's the answer for this one. Okay. Again, as you can tell, again, it's a little more complicated than the previous one in the sense we have a friction here. Well, the friction, to get the friction, you need this direction now. So all these two directions are kind of getting connected because of that. So, and that makes it a little more complicated. You have 3 equations instead of 2 to worry about, but the idea is pretty same, okay? Pretty much same. If you follow this procedure, it almost guarantees that you can solve the problem, okay? So don't feel lost, don't worry about it. Just go ahead and do this procedure, okay? Okay, so we're let's go another one, even a little more complicated, okay? Okay, this time we're gonna let it pull, but we're gonna let it pull from an angle, okay? So we're gonna have a force guy pulling the object like this, but there's an angle here which is 30 degrees, okay? Well, everything else stays the same. So you have F equals to 5 Newton and M equal to 3 kilogram, and then mu K is 0.1. These are all the same, but the difference is you have the force pulling at an angle 30 degrees, okay? But the idea is the same. You still draw this free body diagram. Again, the forces are going to be the same. You have weight, normal force, friction, and this pulling force, okay? Okay, if you put them in the coordinate system, it looks like this. So the angle here is 30 degrees, okay? Now here we have a new problem. It's a little different than before because now we have a force that's not either on the x direction or y direction, okay? As we know, if we want to apply Newton's law, we only apply them to the coordinates, to each direction or each components. So for that purpose, we have to first find out the component of this F here, okay? Otherwise, we won't be able to do proceed. So you see that what we learned from the previous chapter about finding the component vector is useful now, okay? So that's what I'm saying in that chapter, that this stuff is useful for later chapters. This is the case, okay? Now, how do we find out the component? Okay, you need to remind yourself the stuff like this, right? So again, if you have this table, I mean, like the piece of paper putting on the wall next to your bed, probably you already know this by now, but so again, this is your 30 degrees. So this is your Fx, this is your Fy, right? Now use trigonometry, right? For Fx, this is adjacent. So adjacent divided by hypotenuse is the cosine, right? So Fx equals to F times cosine 30. And Fy is the opposite. So Fy equals to F times sine 30. So adjacent divided by hypotenuse, opposite divided by hypotenuse. So you have this two there, okay? So, and that's how you find out the components, okay? Now, after you find them out, okay, you could just write them down. I mean, you could, if you want, it's better, I mean, it may be better to draw another free body diagram. Instead of drawing the original force, you could draw these two components there. It makes things even clearer, more clear. So X and Y. And actually, it's a lot of time, you don't need to draw the original box here to make it a little bit less messy here. So you have, for example, this fx is going to be going along the x direction, right? Fx here, we have fk going to the negative direction, and then we have normal, gravity going down, normal force going up, and then fy going up. So we have two forces going up, okay, one force going down, fk going to left, fx going to right. So we have all these 5 forces. Okay, so now they are either along the x direction or y direction, right? We instead of considering this original f, we consider these two components. They're equivalent because f equal to fx plus fy. So we can write down our Newton's law. Again, along the x direction, we should have, okay, I got a message here. Okay, you can calculate fx. I haven't calculated that yet, so let's wait. So, okay, so, okay, another message. Oh, fy, okay, that's good. Okay, so let's write down Newton's law, right? So along the x direction, right, we have, again, you can write this to kind of remind yourself, this is Newton's law, right? F equal to ma, right? Along the x direction, we have fx minus f. So I'm going to write f cosine 30 minus fk equals to ma. Along the y direction, we have fy, which is f sine 30 plus normal force n minus mg. And there's no x region, so it's 0. Okay? And then we also know fk equals to mu k times n. Okay, so we got these 3 equations. Okay, 2 of them from Newton's law. The third one is from friction itself. Okay, so again, we try to solve them, right? So our goal is to solve a. For that purpose, we know fk, so we need to solve for 3. And then for that purpose, we need to know n, so we need to do 2 first. So let's start from equation 2 here. Okay, so from equation 2, n equals to mg minus f sine 30. Okay. So, and that's gonna be, again, now we need to do some new calculation because we have this second term. So 3 kilogram times 9.8 meter per second squared. That's what we had before. Minus f times sine 30. F is 5 Newton. Sine 30 is 0.5. So this gives you basically 2.5. So 3 times 9.8 is 29.4 Newton minus 2.5 Newton. Okay. So yeah, so fx should be 2.5. You get it right. Yes. No. Yeah. It's. Oh, I'm sorry. My bad. I don't know what I'm thinking. This. Hold on. No. This is fy. I'm sorry. This is not what I'm calculating here. Is fy, not fx, right? So, fy is 2.5. Yes. Good. So, and then this gives you basically 26.9 Newton, right? For my, yeah, this is the answer. So this is our normal force. Now we can go to equation 3. Fk equal to mu k times n. So 0.1 times 26.9 Newton. So we got 2.69 Newton. Okay. And then finally, we can go to equation 1. And we got acceleration equals to f cosine theta minus fk, well, and then divided by m. So we can calculate f cosine theta. So it's that we have a 4. Yeah, some people already calculated here. So maybe we can do it here as well. Like this is 5 times cosine 30. This is 5 times sine 30. Well, this is 2.5. Well, cosine 30 is like square root 2 divided by 2. Square root 3 divided by 2. So it's some you already calculated. So let me see. I'll just calculate again. 30 cosine times 5. 4.33, right? So some of you already got it. So 4.33 Newton minus 2.69 Newton divided by 3 kilogram. Okay. Okay, let's see. Yeah, some of you are doing the calculation with me. That's great. You know, this way you can kind of practice, 4.33 minus 2.69 divided by 3. So we have 0.554. 6. Okay, so I'll run up 0.55. Okay, or I'll keep 3 6 figures, 0.547. Okay, meter per second squared. So somebody got like about 3 meter per second. That's probably not right. Oh, the friction, yeah. I don't know. Okay, okay. So I think this what I got is right. Okay. Okay, so again, as you see here, this one is a little bit more complicated than the previous one, because we have a force that's not on X or Y direction, and so that makes it a little more complicated. But I mean, the idea is the same, the only step we need to do here is to find the component of the force. So instead of considering the original force, we consider the two components like this, and actually all these problems are connected, they're, for example, let's say in this case, right, we got the friction here, but if you take the friction mu k to be 0, the fk becomes 0, so you go back to the previous answer, like this one, right? You'll be just, when fk is 0, become f over m to be the previous one. Well, same thing here, the last one here, right? If you take the angle here to be 0 degree, that recovers the previous case. Then cosine 0 is 1, so you have f minus fk divided by m. It's the same formula as this. So they're all connected. In some sense, we're solving like more and more general problems. Okay. Well, if I give you this one as a problem, example 4 directly, well, you feel like it's too complicated. You can always try to simplify so that you can solve for it, right? Like you can go back to saying you can solve the problem when f equal to, there's no angle first, and then even that one you feel complicated, you can go back even further to solve for a frictionless case, and then go back, to the more complicated cases. Okay. Do you have any questions for me? Good. Okay. I know for a lot of you guys, this is the first time you see this kind of problems, and again, for anything new, it takes time to understand it, to absorb stuff, So I guess you guys are really smart, or maybe I'm a really good teacher. So seems like we're good. Okay. Okay. We have one more example to show you guys, and then after that we'll do some exercise. I don't know whether we can do it today. Maybe we'll do it tomorrow. Okay. So the last one here is probably the most complicated one. So this will be example 5. Okay. Example 5. So this time we'll put this object on a ramp. Okay. So they're still on the surface, but the surface tilted. Okay, with degree 30 degree here. Okay. So it's a tilted surface. It's a ramp. And we will apply a force here to pull the object upward, okay? Let's still keep the force to be 5 Newton, okay? We'll see how this object go, okay? So again, we'll have friction on the surface. So we'll have F equal to 5 Newton, M equal to 3 kilogram, and mu K equals to 0.1, okay? So it's still the same kind of setting, but the only difference is now it's on the ramp, okay? So this problem is probably the most complicated problem we will have, okay, in this chapter, okay? We won't go further than that, okay? Okay, so how do we solve this problem? Okay, same thing, we still do free body diagram here, okay? Now, it doesn't matter where the object is, where the objects are, okay? So anyway, so what kind of force do we have? We still have gravity, and then we have a normal force because the contact is surface, right? So which direction does the normal force go? Notice that it does not go vertically, okay? Because normal force is always perpendicular to the surface. So it's gonna go like this. Okay? This is gonna be the direction move. Okay? And then we have this force F going up, pulling it, okay? Now there's another issue here, okay? So we have a friction because this thing's moving. We have a kinetic friction. But the question is, what direction does the friction go, okay? This really depends on where the object move, okay? Now, saying the object has a force pulling on it doesn't necessarily mean that the object is gonna move upward, okay? Because in this case, because it's on the rim, the gravity is kind of gonna pull it down. So it depends on which one's bigger, okay? So, and that is not really even clear for us, which direction does FK go, okay? It could go upward or could go downward, okay? So for a second, let's assume that, let's forget about friction for a second. We can add it in easily later, but let's just focus on these three forces. And then from there, we can see that, okay, again, this one we're looking for A, okay? We can see how it goes, and then we'll add friction in, okay? But there's another issue here. So these things on the rim, right? So next step for us to do is to set up a coordinate system, okay? Now, if we follow our previous way of setting up coordinate system, we'll do it like this, okay? Okay, but there's a problem with this one. The problem is, see, mg is on one of the axes, but neither n or f are in one of the axes. That means we need to find the components for both of them, okay? So there's a lot of work, okay, because we have two forces to worry about, okay? It turns out that when this thing is on the ramp, it's actually, I mean, a lot of cases it's better to set up a coordinate system a little bit differently, okay? So we could set up the coordinate system like this, okay? Again, I guess what I'm drawing here is not really very well, so let me erase it. Okay, and then go back. So what I'm trying to say is this, okay? So we have this block here. You can set up a coordinate system like this, going one direction parallel to the surface, the other direction perpendicular to the surface, okay? Now the advantage of doing that is you see that these two forces are already on each one of the axes. Now the only one is not on the axis is mg. So you actually need to find out the component of mg. That's a single force. It's better than find out the component of both two forces, okay? You save your labor there. So let's do that, okay? Now how do you find out component of mg? You need to know some angle, okay? So the angle given in the problem is the 30 degree, okay? So, okay, so we need to use that. So let me draw it a little bit separately. So if I draw this like this, you know, this is the 30 degree angle. Well, this is this angle right here. This is 90 degrees. So this is our mg here, right? This is the mg, direction mg. Okay, so how do we figure out angles? Okay, well, keep in mind, this is a 90 degree, right? Because the perpendicular, right? The mg vertical. So if this is 30 degree, that means this angle here is 60 degree. Because this two add together plus this one has to be 180 degree, right? This is the sum of the three angles in a triangle. This has to be 180. Now, that means if this is 60 degree, this angle here is 30 degree. Because these two together is 90 degrees. So actually this, what we know is this angle here is 30, okay? Now you could either use 60 or 30 to solve the problem, to find the component, but it's conventional to use the 30 degree because that's the angle given in the problem, okay, like this one. So you can use this one directly. So it's this one, okay? So now let's draw it like a separate angle here, okay? Separate triangle here. So we have a 30 degree right here. See mg, okay, sorry. Let me erase it. So I'm trying to find the component of mg, right? So let me draw mg like this, and then like this. Because this is our mg here, okay? Now this component here is gonna be our x component because this is going on this direction. So I'll call it mgx. This component here is going to be mgy, and this angle here is 30 degrees, right? So because this is 30 degrees. So see, that's how we draw it. Okay. Now again, okay, in this case, to find out mgx, right? The mgx now, this is 90 degrees, right? This is going to be your opposite. Well, mgy here is your adjacent. So we'll write mgx equals to mg times sine 30, and mgy equals to mg times cosine 30. Okay, so the component going along the direction parallel to the ramp is has sine 30, and then the component perpendicular to that surface has cosine 30. Okay, so this is something like that. Okay. Okay, so with that, we could go back to our original free body diagram. I'm going to draw another one, okay, just to make it neater. Okay, so I'm going to draw x direction going this way, y direction go that way. I'm going to have this f going like this, and then mg sine 30 going to the opposite direction, and then along this direction, which is this direction here, I have mg cosine 30, and then the vertical on the top I have n here. Okay, so these are how I put this two four in there. Okay, see, n and f, and then the two component fg. So I have this four here. Okay, now as I said, we don't know we don't know f yet. So how do we know fk? How do we put fk in there? Again, fk will be either going along this direction or that direction, right? It really depends on which one of these forces are bigger, you know, either mg sine theta or f, right? So we can go ahead and calculate mg sine theta to see. So mg sine theta, sine 30 is like 3 times 9.8 times 0.5, okay? So this was something we got before, like 29.4. And times 0.5, you got basically half of this, right? So it's going to be 14.7, okay, Newton. So the x component is 14.7 here, okay? Let me double check. Yes, okay. Well, the y components, I mean, you can go ahead and calculate y component. We need that anyway. So 3 times 9.8 times cosine 30, which is 0.8 something. I always don't remember this number. I know it in the 0.866. Okay. Okay, and then you just do the calculation. You get times 29.4, 25.5. Okay, 25.5. Okay. So basically, we see that this force going down is 14.7. Well, the force going up is only 5. So actually, this force is bigger than this force. So the whole thing is going to go downward. Okay, that means your friction is going to go upward. Okay. So I'm going to put a friction like this. Okay. So even though you have something trying to pull it upward, it's still going down. Okay, because the component gravity is so big. Okay. Okay, so that is our final free body diagram. Okay. And then we can use this to solve our problems. Okay, whatever unknown we want to get. Again, we have 2 Newton's laws, one along each direction. Along the x direction, we have max. And then along y direction, we have may, right? Okay, let's do the first one here. Now we have these forces here. Okay, we have okay, you know what? Let me change our positive direction. Okay, let me put the positive direction going downward. Okay, now again, it doesn't really matter, but it's a little more convenient to define this way because we know our expression going this direction. Okay, so we do this, is going to be positive. Our expression is going to be positive. Okay, so you write it down. You have mg sine 30 minus fk minus f equals to ma. The a is something we want to find out. Along the y direction, we have n minus mg cosine 30. And again, there's no motion along the y direction. So it's another way why we want to set up our coordinates like this, because the expression is only along the x direction. There's no expression along the y direction. you set up like this, you will have both component for acceleration. It's going to be like a mass. Okay. Now, finally, we have Fk equals to mu k times n. Okay. So again, we got these three equations, 1, 2, 3. They're very complicated now, but we can again start from the second one. We'll solve for n, and then we'll go to third one, solve for Fk, and then the first one to solve for a. So the second one, we have n equals to mg cosine 30. Okay, we already got that number. It's right there. So it's going to be 25.5. Okay, 25.5 Newton. Okay. And then we go to the third one. We find Fk. Fk equal to mu k times n, which is a 0.1 times 25.5 Newton. So 2.55 Newton. Okay, that's for Fk. And then finally, we go to part 1 to solve for A. So in this case, A equals to mg sine 30 minus F minus Fk divided by M. So we have a bunch of this. So mg sine 30, as we calculated, is 14.7. And then we have Fk, which is 5 Newton. And then we have, sorry, F is 5 Newton, and Fk is 2.55 Newton divided by 3 kilogram. Okay. So, and then plug all these numbers using calculator, 14.7 minus 5 minus 2.55, okay? And then divided by 3, we got 2.38 meter per second squared, okay? Now it's positive, so based on the definition of our coordinate system, it's going downward, okay? So it makes sense, okay? Does that make sense, you guys? I know this last one must blow your mind away, because it's so complicated, But what I want to point out is, again, if you just carefully follow the steps we have, the procedures, drawing the diagram and setting up a coordinate system, and then find the components and put them on the diagram, and then determine the direction of friction, set up your equation along each direction, you can solve the problem. I won't give you any problem that you cannot solve, okay? And notice that I draw a bunch of diagrams for this one, right? I start from here and then I go here, and then I draw like this one to figure out the angle, and draw another one to figure out the components, and then I put everything together like this. It doesn't matter, okay? The more diagrams you draw, the more figures you draw, the better, the easier the problem will be, okay? So don't be afraid of drawing. I know some people, for some reason, when I teach this class in classroom, a lot of people, when they solve the problem, they just don't know. They don't draw anything. Just sit there and look at the problem. It won't help, okay? Our brain is designed that it won't manipulate numbers very quickly, process numbers quickly, or figures just in your head. It's designed that you have to put something in front of you, you have something specific to look at. Then it's easier for the brain to figure out, to do analysis. Our brain is really good at doing analysis, not good at memorizing, and especially a lot of things together, put everything together. It's not good at doing that. So again, try to draw as many figures as you can. Try to draw as many diagrams as you can for these problems, okay? Does that make sense, you guys? So all these 5 problems, they're really good problems. I want you guys to go back and to study those 5 problems and then study them like one by one. I mean, you can try to solve them by yourself. I mean, starting from the first one, using the procedure I gave you, and then move on to the next one until you feel some difficulty, and then you look at the solution and see what the problem is. These problems are really good problems in the sense that they go in a series. So it kind of help you to see how do you go from like a simple problem to a difficult problem, like that, So try to study them, and so that you can understand what's going on, okay?